1. Introduction to climate change. In this two-part climate feature, we bring you up to date with the latest research and findings about global climate change. In Part 1, we discuss the problem and take a look at some of the changes we can expect. Part 1 also lays the groundwork for a better understanding of the measurements and methods used to arrive at conclusions about climate change that we'll be discussing in Part 2. In that article, we'll review what's happening with our ice caps and oceans, and we'll examine how climate scientists make their predictions and why we should pay attention to what they're telling us. So, if you've ever wondered about the scientific basis for the predictions about global warming, climate change, and their predicted effects, these articles are for you. They're an introduction to that vast area of science, and show just how much we have yet to learn about our extraordinary planet, and how much we need to learn and fast. Without a doubt, global climate change is a hot topic. Our world is getting warmer. In some parts of our planet, the change shows up as drier and warmer weather, leading to serious water shortages and damaging fires. In other areas, it manifests as wetter conditions which lead to downpours, floods, and mudslides. We are seeing an increase in the frequency and severity of extreme weather events. All of this has given rise to a growing sense of unease, as more and more scientists predict the coming of devastating impacts of climate change. We are already grappling with the problem of fractured governments and international indifference to the loss of life and property wrought by some of these catastrophic events. The growing frequency of these disruptions, coupled with the problems associated with their short and long-term fixes, could spell disaster well before we feel the full force of climate change. Definition and causes of climate change. The primary human activities that are releasing CO2 in the atmosphere are the use of fossil fuel, like oil, natural gas, and coal, as the primary means of producing energy, deforestation, industrial processes, and some agricultural practices. A number of natural processes release CO2 and other greenhouse gases in the atmosphere too, which includes gas, fresh oil, and coal extraction and use, biological decay, volcanic eruptions, and forest fires. However, the carbon that has accumulated in the Earth's surface over hundreds of millions of years in coal, oil, and gas deposits, and which would release CO2 slowly through natural processes if they were not being extracted, processed, and burned, is being released at an accelerated pace by humans. The fact that natural processes have taken millions of years to accumulate underground carbon that humans are releasing in decades, often through processes that damage ecosystems and the environment, giving rise to additional environmental and economic problems, is at the core of the problem facing the world today. Climate change refers to significant long-term fluctuations in temperature, precipitation, wind, and other elements of the Earth's climate system. Climate change is caused by certain human activities which have been altering the chemical composition of the atmosphere through the buildup of greenhouse gases, especially carbon dioxide, methane, and nitrous oxide. Energy from the sun drives the Earth's weather and climate and heats the Earth's surface. The Earth's surface gives off energy into the atmosphere. Greenhouse gases such as water vapor, carbon dioxide, methane, nitrous oxide, and ozone in the atmosphere are transparent to some kinds of infrared radiation, but dense to others. This property allows these gases to capture infrared radiation that the Earth sends back into space. These greenhouse gases absorb energy and then re-radiate it in all directions, heating the Earth's surface and the Earth's overlying atmospheric layers. This is a natural process that has enabled the Earth to be warm enough to support life as we know it. Historical context and impact. These contexts underscore an important reality. Earth's dynamic environment encompasses timescales from seconds to billions of years, and space scales from microscopic to planetary. These environmental attributes reflect the combined effects of interacting systems at many scales, ranging from biogeochemical to biogeographical, tectonic to technological, and nanoscale to planet-wide. However, as a general rule, when people today refer to global change or environmental change, they usually refer to processes, phenomena, measurements, analysis, policy, and so on centennial to millennial scales. The climate system of planet Earth, and the environment and ecosystem in which humans and other species live, have experienced dynamic changes over the broad sweep of planetary history. Many of the major features of our global environment, as well as key resources needed to support the economy, culture, and social interaction of human civilization, have been shaped by a continuing history of change. This backdrop of Earth history is intrinsic to scientific understanding of the current and possible future character of global and regional climates, the geophysical and ecological impacts associated with natural or anthropogenic climate change, and the history and consequences of policy debates and other actions aimed at promoting public welfare in the context of impacts or risks related to climate variability and change. Current global climate trends. The report is based on the latest research and findings, and includes many of the areas listed below, while adding new indicators that have become a priority to report on, due to recent developments and observations. This version, therefore, presents a comprehensive account of the Earth's climate, the increasing levels of human influence on the climate, as well as the reported impacts on socio-economic and environmental systems that are vulnerable to such changes, and the occurrence of weather and climate-related disasters. Various methods are used to investigate present-day climate, including the development of computer-generated climate models, measurements taken on Earth, and observational data of systems in space. These observations give us an understanding of the complex interactions that are at play in the Earth's atmosphere, oceans, and on the land's surface. Indicators are then generated from the observations to monitor and understand the Earth's climate system, which has significant climatic, environmental, economic, and social impacts. The indicators are referred to in the report that follows and offer an entire picture of the Earth's climate system and its variability. Temperature changes. The global mean temperature for the years 2016 to 2020 is therefore around 1.2 degrees Celsius higher than the likely range of 1850 to 1900. The likelihood of any single year of this 5-year period being the warmest of all is less than 25%. Because temperatures of individual years tend to fluctuate, this probability is low, but when we compare the temperature of this 5-year period to any 5-year period since 1850, it becomes very high. There is more than a 99% probability that this level was the highest of all. The year 2020 turned out to be, on average, the second hottest year since 1850, when instrumental record-keeping began. The last 2 decades of temperature data have all been the hottest since the record began, and the last 6 years, 2015 to 2020, have been the 6 hottest years on record. If the current trend continues, we are likely to break national temperature records over the next 5 years. A year-long global average annual temperature, approximately 1 degree Celsius above the pre-industrial era, around 1850, makes globally coordinated efforts not only important for the future, but also urgent. Extreme weather events. Most of the world, including China, will have substantially more than 1 degree of warming by mid-century, and will be at high risk of changes in regional extreme weather events. This poses serious challenges to sustainable development in various fields such as environmental systems, resource usage, food security, and human society. Therefore, it is very important to understand future climate change risks. It's time to get serious about preparing for risks, as discretion is inevitable in the context of future changes, and current visions and decision-making may affect individual and social well-being and continued prosperity. Such a future realistic view requires better tools and interactions of natural and social sciences. At the end of the Anthropocene, much remains to be understood, and much remains to be built. The future is still ours. This article briefly summarizes selected papers in the special issue of Climate Change Progress in China. They provide a diverse and comprehensive insight that captures important research advances and novelties and/or improvement of existing scientific approaches or applications, with relevance to a wide range of key climate change and environmental issues related to extreme weather events in China. The changes in the physical climate system and climate system working together have led to an increased occurrence of extreme weather events, which has been widely recognized. Due to the complexity of the natural ecosystem, The climate system can provide various physical and chemical conditions for the production and survival of different organisms, and make corresponding physical and chemical environment changes. It has been reported that anthropogenic climate changes have led to an increase in extreme heat, drought, and heavy precipitation events in major regions of the world. In the longer term, these changes may become increasingly irreversible. Without adaptation and mitigation measures, the increase in extreme weather events will likely increase the likelihood of serious adverse effects and exacerbate affected areas or conditions. In this special issue, Climate Change Progress in China, we present a collection of papers that provide new insights and scientific evidence into various extreme weather events and investigate the possible driving factors, climatic and otherwise. Key climate change indicators. The largest warming trends have gone through 3 versions of the permafrost-based surface air temperature history, and there is additional evidence that a large permafrost region warming is also present in inversions of temperature measured at boreholes in Greenland. Although late winter inversions have much more warming than is observed on the surrounding ocean, the meteorological causes of these warming signatures are still a topic of active research. At least some of the winter-spring warming can be attributed to fixed dynamical factors, including a persistently high-pressure center located off the east coast of Greenland, which acts to block and divert weather systems poleward and reduces the equatorward heat advection from the south. Climate models have difficulty featuring this sort of variability, partly owing to unresolved complexities, which can be simulated to some extent on the industrial cluster. Model results and on-the-ground observations are analyzed in context of surface conditions such as inversion layer depth, the strength of the inversion aloft, and cloud cover. The Arctic's changing continents over the past 3 decades, the rate of warming in the Arctic has been almost twice the global average. In particular, the northernmost portion of the Arctic, above the 67th parallel, has been warming at about 3 times the global rate. Arctic sea ice has been retreating and thinning. Between 1979 and 2002, the summer ice extent declined by about 15.6% per decade, with the decline accelerating throughout the period. Since 2002, the record low extent for this period was set in 2002, a 49% below the average ice extent for 1979 to 2000. In 2005, the record minimum in minimum Arctic sea ice extent was broken in September, breaking the 2002 record by 20%. The trend continued in 2007, with the record minimum in minimum sea ice continuing to shrink by about 24% below the 2005 record minimum. Preliminary data suggest ice extent could reach a new minimum in 2008, for the 3rd year in a row. Greenhouse gas emissions. Established energy and GHG traits in particular show little capacity to project trends, increasingly diverging from the elastic model. Thus, our conclusions about expected net zero GHG characteristics using established methods should be treated with caution, as many describe trends consistent with future net positive emissions. We imagine instead the required technological change firstly innovating emissions reductions from existing infrastructure, but increasingly shifting capital formation and resource use towards net zero investment, past the mid-century threshold when lowest cost net zero greenhouse gases are visualized. No country would any longer have access to a purported carbon budget conditional on postponing mitigation, considering a future of substantially higher energy and GHG elasticities over the next few decades, a potentially strange illustration of entropy economics. Introduction. Greenhouse gas (GHG) emissions are driving climate change. Beyond the emissions reductions pledged by countries for the Paris Agreement, new technologies or changes in investment and consumption patterns have the potential to drive emissions downwards on an unprecedented scale. In this chapter, we summarize the latest GHG estimates and explore a range of evidence on drivers that already exist or promise to deliver rapid and deep emission cuts, resulting directly from new mitigation opportunities, shifting investment and increasing returns, and changes in the price and cost system at the heart of the economy. We focus on the role of technological change. Our main sources of information include a global panel of GHG emissions, socioeconomic and environmental statistics, and a novel database with data about over 2,000 climate-relevant academic articles published since 2016. The results make clear that meeting the most ambitious aims of the Paris Agreement and beyond is feasible, but will require overcoming profound barriers that have not yet received sufficient attention. Sea level rise. It also provides an extensive discussion of these and other uncertainty sources, including the relative dearth of studies considering some geophysical feedbacks that could increase future sea level rise beyond current understanding. Policymakers, planners, or other users already have access to a set of direct applications of hazard mapping, such as spatial targeting of investment and regulation, and identifying the links between anthropogenic greenhouse gas emissions. But broader issues about the emerging science with risks and opportunities that could help shape future discussions and policy decisions are less well recognized. These and many other questions could have dramatic impacts on future decision-making across a broad range of sectors, including national and infrastructure security, economic planning, land use, and environmental protection. But with different implications for modeling flood hazards in hazard mitigation policy, current studies are often narrowly focused, ignoring other potentially important drivers such as local sea level rise, changes in tides, storminess, and the role of natural variability. This paper reviews research and projections regarding future uncertainty in global predictions, and examines the projections of local and regional relative sea level changes as uncertainties occur. Sea level rise has emerged as one of the most visible and devastating impacts of climate change, with numerous studies documenting how even small increases can exacerbate flooding, storm surges, and other impacts. Yet uncertainties abound, including future scenario development, the impacts of uncertainty on results, differences in model projections and observational trends, and the role of policy choices on maximum sea level rise. Latest research on climate change. So, the significant findings that have been published in the intervening period largely reinforce the insights and conclusions from the previous synthesis reports, as well as the first order, 4 special reports from Working Group 1, and the special report on land use and climate, and the contributions of the 3 working groups for the upcoming 6th assessment report. Open peer review, under the careful stewardship of a large team of review editors, has strengthened the impact of the reports and improved the accuracy and precision of the findings. Over the past 3 years, the Intergovernmental Panel on Climate Change, IPCC, has published 2 special reports on the more ambitious target of limiting warming to 1.5 degrees Celsius. In parallel, other research and evidence building has continued, including research on increasing public understanding and the merits of behavioral approaches. This chapter offers a non-exhaustive summary of recent findings, with the next chapter addressing the question of where this leaves us in terms of action. For the most part, this research reinforces earlier findings, but the urgency and, as a result, the attention that is brought to bear on certain individual issues have certainly evolved. Climate models and projections. Climate GCMs, global climate models, are considered the most complete expression of our understanding of climate processes. Their outputs are detailed, covering all regions and variables of interest. The number of GCMs used in the IPCC, Intergovernmental Panel on Climate Change assessments, has increased since the first. The IPCC AR5, Assessment Report 5, included an intercomparison exercise that involved an ensemble of simulations using 24 GCMs for 2 periods, the first representing conditions in 1986 to 2005, and the second 2081 to 2100. Also used were 4 greenhouse gas concentration pathways plus an additional case where it is assumed that concentrations are stabilized. Preliminary simulations of different greenhouse gas emission scenarios showed that the climate system responds globally and uniformly, regardless of the emission source. The retreat of glaciers, however, responds instead to regional scale variations in temperature and precipitation. Other different modeling approaches agree that any scenario of future changes suggests that a severely aggressive emission cut may only benefit the distant future, with a timing that particularly favors some mitigation measures. Anthropogenic climate change results from increases in the concentration of greenhouse gases in the atmosphere. Predicting how future emissions may influence the climate requires complex models that formulate the behavior of the atmosphere, ocean, land masses, and ice sheets. Models produce future projections of several variables, including air temperature and precipitation. These projections vary, depending on the assumed composition of the atmosphere. Therefore, scientists often run several models with scenarios to do with various trajectories of greenhouse gas emissions. Biodiversity loss. The losses of biodiversity have also been compounded by a long-term global trend that is driving climate change, our increasing dependence on fossil fuels. Stabilizing the concentration of atmospheric greenhouse gases through emission reductions that are needed to slow and eventually reverse climate change will not come without costs, and there may be victims. Yet, the benefits of mitigating climate change are so high that we must not make this decision with blinders on. In some cases, global climate change may accelerate local species loss by making pre-existing threats worse. In other instances, local environmental changes may actually slow the global loss of biodiversity. Now, a global reduction in greenhouse gases may benefit some but not all species. The loss of biodiversity is one of the most important concerns for humankind because the living creatures and natural areas provide ecological goods and services to human beings. Pollution, deforestation, global warming, and overuse of the natural resources are the noticeable manifestations of the loss. Human activities are expanding beyond the Earth's natural carrying capacity. Many wild places, their indigenous plants and animals, as well as their wilderness values, are threatened. The potential disappearance of many unique and colorful species of plants and animals will not be the only impact of global warming on Hawaiian biodiversity. Coral reefs, for instance, are also gravely endangered by climate change, with projections indicating that 30 to 80% of all coral reefs could be lost in the next 20 years. Mitigation and adaptation strategies. Like a shipload of largely empty barrels drifting close together, the failure of global leaders to mount any meaningful response to the gravest crisis faced by our planet in ecological time should make us question our own moral fitness. True, there are some nascent efforts to reduce greenhouse gas emissions, especially through increased energy efficiency and the rapid expansion in both developed and developing nations of renewable energy sources, particularly wind and solar. However, given the greatly increased standard of living in India, Brazil, and China, and the projected continued heavy use of coal for the foreseeable future by the USA and many other nations, the aggressive changes needed to address the avalanche of current and anticipated drought, famine, disease, and human migrations require more robust governmental leadership. Most experts anticipate significant global warming in the 21st century. Efforts to mitigate global warming include the Kyoto Protocol, an international treaty to reduce the greenhouse gas emissions that contribute to global warming, and geoengineering, which uses large-scale human intervention to reduce the rate of warming. Technical approaches for geoengineering include blocking incoming sunlight by releasing reflective particles into the upper atmosphere or by placing mirrors in space. Another technique is to stimulate the ocean's uptake of carbon, enhancing the flows of naturally occurring processes. Many experts note that adaptation is required to address the changing climate, and that there are significant limits to mitigation. Renewable energy technologies. From mid-1999 through 2007, U.S. wind capacity grew from approximately 2,500 megawatts to over 16,500 megawatts of grid-connected electrical generation capacity, a compound annual growth rate of over 27%. In 2008, its growth rate exceeded 50%, and in 2009, 10,000 megawatts of new wind capacity are scheduled to be installed. The rapid upward trend in wind capacity is evident, and as higher capacity factor windmills, transmission, electric storage, and supergrid initiatives continue to be developed, further increases in wind generation can be expected. Despite the tremendous strides wind power has made in the US, it still accounts for only a small portion of total US electricity consumption, about 20 bkWh per year. EU and China also recognize the potential value of wind energy and are working to develop their own large-scale wind power programs. Although variable, the energy potential for wind is enormous. Interpolating the data from the map provided by NREL, completely blanketing the 12-mile area off the east coast from Maine to Florida, with 7 megawatts wind turbines, would yield about 3,600 BKW of average electrical power. A similar imaginary area located along the coast of Texas, over 3,000 BKW, East Coast over 3,000 BKW, and Michigan over 2,500 BKW, and on existing federal lands in Nevada, Arizona, New Mexico, and Utah, nearly 5,500 BKW, maintain the U.S. on a constant, uninterrupted renewable electrical diet. Provided that modest local and regional energy storage or supergrid interconnection is associated with wind power installations, about 200,000 turbines would be more than enough to provide the U.S. with sufficient electricity to meet commercial, industrial, and residential demand. Renewable energy technologies, wind, solar, biomass, hydro, and geothermal, represent a tremendous opportunity for the generation of affordable and pollutant-free electricity and heating for commercial, residential, and industrial use. In 2007, renewable energy constituted approximately 6% of total U.S. energy consumption, with hydroelectric power accounting for nearly 3/4 of the total. Biomass and wind technologies accounted for approximately 1% each. Despite its promise, other renewable energy technologies contributed very little to the total energy mix. Despite this, renewable energy technologies are surging to fill the void created by years of skyrocketing prices in the fossil energy market. Once largely viewed as a supplement to conventional energy technologies, wind power-generated electricity is beginning to displace base load plants, and commercial industry is increasingly viewing solar technologies such as passive solar, photovoltaic and concentrating solar power technologies capable of delivering grid-quality electricity. Large-scale biomass power plants and the use of ethanol as a gasoline substitute can also be dispatched to meet base load needs. Climate-resilient infrastructure. This document provides an update on global climate action and is supported by slides from the report. The first chapter discusses climate-resilient infrastructure. The authors undertake a review of more than 70 studies that estimated long-term economic impacts of infrastructural investment and found that the reduction in the risk of climate hazards is significant. The review once again brings to light the sheer size of infrastructure investments that will be needed just to bring these regions to a critical minimum level of infrastructure. Already severely strained infrastructure will experience even more delays, outages, and expenses during climate hazards. The report outlines a strategy for making existing and new infrastructure climate resilient. Climate resilient infrastructure is a major priority for all countries. With regard to existing infrastructure, retrofitting to make it more resilient is an immediate priority. For new infrastructure, greenfield projects need to factor in climate change. Awareness about the potential impact of a change in climate on infrastructure is essential from both the demand and supply side. Availability of space in cities for regulatory or risk-sensitive land use planning is key to protecting urban infrastructure from natural disasters. As with existing infrastructure, primary stress points in any city, such as flash flood zones of urban rivers, need special attention. International agreements and policies. The protocol defined legally binding emissions targets for developed countries, but not for developing countries like China, Brazil, Indonesia, and many other countries in Latin America. Even if the countries under the Kyoto Protocol met their obligations, their total emissions made up less than half of the global total by 2009, since China, India, and many other non-Annex I countries would be contributing to the majority of greenhouse gas emissions and would therefore be doing most of the damage. With developing countries surpassing the emissions of the countries with reduction obligations, legally binding emissions reduction obligations, targeting developed and non-Annex I countries became a requirement. Agreements to reduce current and future greenhouse gas emissions have been made at the international level. These include the 1997 Kyoto Protocol to the 1992 United Nations Framework Convention on Climate Change, Kyoto Protocol, and subsequent agreements. Under this agreement, countries were assigned agreed amounts of emissions that they were allowed to release within specific time periods. Some countries' commitments ended in 2012. After that date, 194 countries under the COP21 agreement have varying industry and country-specific climate commitments. Paris Agreement. I have actively participated in global climate change negotiations since 1989. After more than 25 years of being immersed in this complex process, involving global geopolitics, national interests, economics and sustainability, I must declare that the Agenda 2030, adopted in 2015, and Paris Agreement outcomes are remarkable. But the journey to reach these milestones is also an example of diplomacy that often goes unnoticed. After Part 1 of this book introduced climate change, its multiple effects on natural and social systems, and the urgent need to react to it, Part 2 explains the background and contents of the United Nations Framework Convention on Climate Change, UNFCCC, the Kyoto Protocol, and the Doha Amendment. Part 3, in turn, explains the Paris Agreement of 2015 in detail, along with the progress produced in its implementation. First introduce the problem, its effects and what causes it. The 2015 Paris Agreement was the first UN under 2-degree multilateral agreement on climate. That is, it asks parties to commit to a maximum 2 degrees Celsius temperature rise, and to pursue efforts to limit the temperature increase to 1.5 degrees Celsius above pre-industrial levels. In Paris, parties agreed to hold the increase in global average temperature to well below 2 degrees Celsius above pre-industrial levels, and to pursue efforts to limit the temperature increase to 1.5 degrees Celsius above pre-industrial levels, Article 2, with 1.5 to 2 degrees Celsius central goal, and to undertake rapid reductions thereafter, so as to achieve a balance between emissions by sources and removals by sinks in the second half of the century, Article 4. The agreement marked a move away from the strict division between developed and developing countries, used in the United Nations Framework Convention on Climate Change, towards a more flexible classification. It confirmed that all parties should take action, and specified that developed countries should provide financial support to help developing countries meet their commitments. United Nations Framework Convention on Climate Change. The UNFCCC has the status of a constitution in the climate system. On the basis of this constitutional framework, subsidiary agreements are negotiated. The two most important subsidiary documents today are the Kyoto Protocol and the Marrakesh Accords, which together constitute the COP and CMP track, according to Article 15, paragraph 13 of the UNFCCC. The basis of all negotiations is the adoption of decisions concerning further rules and the targets and timetables of greenhouse gas emissions as the central theme of the Kyoto Protocol and today's negotiations. The UNFCCC and its Kyoto Protocol entered into force on February 16, 2005. The other major international environmental treaty of UNCED was the Convention on Biological Diversity, which has largely been marginalized by UNFCCC-related climate cooperation. The United Nations Framework Convention on Climate Change, UNFCCC, is an international environmental treaty adopted at the United Nations Conference on Environment and Development, UNCED, in Rio de Janeiro in 1992. The UNFCCC objective is to stabilize greenhouse gas concentrations in the atmosphere at a level that would prevent dangerous anthropogenic interference with the climate system. The UNFCCC is a framework document that, among other things, contains no detailed rules or solutions for its implementation. The role of science communication. The panel members agreed that the Paris Agreement not only sends a powerful signal about the world's determination to fulfill the UNFCCC's ultimate objective, but it also confirms that scientific research on climate change has reached a stage where more robust and detailed policy advice can be provided, and more and better science communication should be pursued. Participants thus noted that the agreement ushered in a new era in international climate negotiations, with the focus shifting from climate change to climate risk and from avoiding impacts to managing them. The discussion also identified a significant role for national and semi-national science academies in this context, which is a future task for science academies. Science communication plays a vital role in addressing the challenge that climate change poses. It is essential to ensure that in their daily operations and in their long-term planning, all decision-makers have the necessary information. This is as true for business leaders and investors as it is for local authorities, government officials, and non-governmental organizations. The Achieving the Paris Agreement Science and Policy Dialogue at Harnack House in Berlin, in November 2016, discussed the topic. 4 panelists outlined their views and a lively exchange of ideas followed. Public perception and awareness. Funded by the Department for Environment, Food and Rural Affairs, the UK Climate Impacts Programme aims to raise awareness, encourage the assessment of impacts, and build capability for adaptation to possible future changes in the UK climate. Following completion of an awareness and uptake consultation, a survey of organisations engaged in activities relevant to climate change was undertaken. The findings suggest that environmental practitioners tend to have a working knowledge or competency, while local government, business and community organisations do not. Reliance on existing funder prioritisation to take account of climate change has been the prevailing approach. Knowledge comes mainly from the mass media. Given that the physical effects of climate change are far-reaching with significant implications for communities and businesses, especially for infrastructure and insurance, these findings suggest that no specific policies focused on environmental damage trigger residents to mitigate effectively or prepare, adapt for those changes. Such regulations should be designed as informational response regulation to coordinate the necessary living adjustments at a lesser cost. Media coverage of climate change. The recent focus of climate change problems within the UK has centred around a controversial third runway at Heathrow. The majority of the media grouped themselves around this. The general public's sympathies lay with the green perspective of lagging a long distance behind, above the industry view. People, rather than businesses and those concerned about jobs, were framed as those who will suffer. Only the most vocal of these managed to represent the health arguments against the runway. However, on some occasions skeptics' views were highlighted, including the industry view from groups like Wings WWFC. Other skeptics have also been given space on the radio, in one well-known case an hour's worth of airtime with the then-new director of the Tyndall Centre. Their reports were cited as external universities by newspapers. Filmmaking for the opposition to the runway also draws on research findings from universities, although its coverage was not as extensive. Economics, cost and job numbers for the runway were the main focus for media. Attacks, challenges and questioning were raised. Footage from the protest movement was caught on film to be used as part of a documentary earlier in the year, and at least one reporter protested. It appears, though, that some of the media have sway on public opinion, where some can be sites of controversy. Media coverage of climate change has, however, been heavily influenced by skeptic arguments. As some advertisers on TV or in the press share sentiments akin to the skeptics, they offer a more sympathetic ear to these arguments. In 2004, most of these existed in the UK. Over a quarter of the articles in a week in March of that year showed some measure of skepticism in stories. Comment pieces continue to support skeptics' beliefs. Research in this field is currently limited, but highlights that some media outlets are sympathetic to the skeptics' arguments. This is only a facet of coverage, however, as most of the quality press became frazzled, frustrated, and were openly contemptuous of skeptics, particularly after the shock of extreme weather events such as the heatwave and wet summer in 2007 hit the UK. Slow and gradual impacts of climate change may not elicit such responses. These in part arose from the diversity of framing within the media that became evident when examining the coverage of the UK's Stern Review on the economics of climate change. While many outlets in the public's eye positioned the review as a costly intervention, others believed that the report signalled the need for urgent and radical action. Some even thought the review represented a missed opportunity for more vigor to address climate change. Our own research found no sign of skeptics' voices in consideration of the review. Conclusion and future directions. We offer 2 suggestions to address this. Critical engagement with political crackdowns and social reaction to outmigration, including the enforcement of migration controls and perpetration of violence, can also be infused into security analysis. The writing and circulation of global climate policies is underpinned by a largely operational discourse that conceptualizes the permissibility of these policies and the links connecting these mechanisms as objective, normative, or legal. As climate change and migration, along with other global issues such as development and security, arise as principal political issues more broadly, critical climate and migration research must also expand and adapt to engage with the often manipulative or complex ways by which issues become politicized in settings where leaders and communities compete for power and resources. The findings presented here provide a snapshot of the vast, varied, and dynamic research and policy literature on climate-migration relationships and related topics. However, there is much more work to be done moving forward. Our understanding of human responses to climate change, in its broadest sense, can benefit immensely from further empirical and theoretical research in the context of predictions that vast numbers of people will move due to environmental change in the years and decades ahead. As we discuss further below, advancing basic theoretical approaches to migration can help underpin and improve the accuracy of empirical research efforts. Limited theoretical contributions in the climate migration literature hinder our ability to generate contextually salient impacts for specific locations at risk of migration driven by climate-induced shocks and stressor. Challenges and opportunities in climate research. The body of evidence in support of these changes is substantial and has not been undermined, despite claims to the contrary. It is based on data of all kinds: air temperatures, ocean heat content, humidity, cloud patterns, growing season changes, vegetative greening, snow cover, sea level rise, hurricane and typhoon intensity, fire and flooding patterns, and more. Furthermore, it comes from multiple groups analyzing these data and develops over time. It inevitably demonstrates the reasonable questions about the completeness and accuracy of the global climate record are indeed useful to the scientific monitoring enterprise. However, these challenges, especially after being repeatedly asked and ever more thoroughly answered, start to reek of obstructionism rather than healthy scientific skepticism. On the other hand, science is never dogmatic, rather it regularly tests conventional wisdom and revises itself when new facts so dictate. The growth of the scientific basis of climate change has been no exception. The story of that growth, especially the discrepancies, feedbacks, and successes in the observation and modeling of climate system elements and interactions, is chock full of interesting and important insights. Scientific understanding of human-induced climate change is based on unprecedented amounts of observational data, ever-improving models, and a thorough understanding of all relevant effects. In the more than 30 years since the issue arose, various lines of evidence have emerged, serving to establish that warming of the Earth's climate system started about 1650 and has accelerated into recent decades. The observed increases in global mean surface temperature are, moreover, scientifically debated, and understanding has evolved, linking those increases to human activities, primarily burning of fossil fuels, industrial processes, and land use changes, through a variety of plausible mechanisms which have been corroborated by studies showing that natural factors are either incapable of causing warming or have led to cooling over the past half-century. Call to action for individuals and governments. We, as global citizens, cannot allow the continued destruction of our only biosphere. We must all work tirelessly to force governments and corporations to not only have environmental policies, but also to enforce these policies. We cannot allow our Earth to be destroyed for the profit of bounty and greed for the few. The natural ethic of valuing and protecting nature cannot be relegated to environmental conservation, nor to those in the alternative lifestyle. It must become an ethic of respect for all forms of life on the planet. The human race as a species has evolved from the survival of the fittest race to today's diverse and compassionate global citizens. Never in the history of humanity can people ignore the plight of their fellow beings, no matter where they live on the globe. The combination of globalization and the internet has brought much of the world into every home and has forced the world to no longer be blind to individuals and governments who are indifferent, callous or tolerant of human injustice, no matter how far or near off the Earth's physical boundaries.